On to page number 16. And looking at examples of esterification. First one is of ethanol and ethanoic acid. So what we're going to do underneath that equation, yes, you've got the equation, and we want to write our structural equation in Oshin. Okay, so generally what we'll do for this example is draw our ethanoic acid first. Generally we use the alcohol first, but we'll talk about that when we get to that. But again, we need our colour coding here for our different chains to show which chains come from which part, either the acid or the alcohol. Okay, so first of all, it's got ethanoic acid. So I'm going to do my carbon chain in pink or red, whatever colour this is. So that's my ethanoic acid. Then I'll just go back to my normal black pen for the carbonyl group. But then I'm going to do the OH of the carboxylic acid in blue. And you'll see why I do that in a second. So this is ethanoic acid. And I'm going to use the same colour that I used for the carbon chain of my acid. So this is ethanoic acid plus ethanol. And I'm going to pick a different colour for my ethanol chain. So I'm going to do it in green. You can do it in all black pen and then highlight in different colours if you want, but whatever is easier. Okay, that oxygen is in black, but that hydrogen should be in blue. Okay, and again, I'll write ethanol in the colour that I've used for the carbon chain. Okay. Now, this reaction is reversible when we do them under these conditions. So we'll use an equilibrium arrow. And then we will draw what we end up with. The reason I've drawn those, that oxygen and those hydrogens in blue is because those are the atoms that we lose. So if there's one oxygen, two hydrogens, what do you think we lose?
Water.
Water, great. So those are the particular molecules that the water come off. So again, we'll draw out our chain. Okay, and this is our ester link. Oh, wrong colour. And then just our chain from our alcohol connected to the singly bonded oxygen. Okay, and then we've lost a water molecule, so we'll draw that in our blue to show which particular atoms they came from. So you can see basically my ethanol and my ethanoic acid have just added together at that acid position. We've just swapped the hydrogen of the acid, so to speak, with the carbon chain of our alcohol. But to name it, we need to be really careful. In this case, we don't need to be careful because we've got ethanol and ethanoic acid, so it's not going to affect the name, but we'll look at that in our next example. How we name this is we name it as, and as it says there in your notes, as an alkyl carboxylate. The alkyl part of the name comes from our alcohol. So these can be quite confusing if you get them mixed up, but how I think of it is alcohol, they kind of sound the same. So the alkyl part comes from the alcohol, and so it's going to be ethyl because I've got ethanol. So this is ethyl, so if you write that in the colour that you've used for your alcohol chain. And then carboxylate. So again, I look at the length of my carboxylic acid, and it's F as well, and so I call that ethanoate. Yeah.
The thing above the water is ethanoate.
Yeah, yeah. Okay, so the green part at the start, the ethyl, comes from the name of the alcohol, and the ethanoate comes from the acid, and yes, it does matter. Not in this case because both are the same length, but in the next example when we see they're different lengths, it will matter. Alright, so let's look at the example of propanol and methanoic acid. So first of all, draw your structure of propanol, again using the colours that you used previously. So this is propanol plus methanoic acid. And so I use green for my alcohol chain, so I'm going to stick with that. That oxygen is in black and the other one, the hydrogen, should be in blue. Okay, to show that that comes off when we form our water. Okay, so there's our propanol. Plus our methanoic acid. So be careful about your methanoic acid. It's only going to have one hydrogen coming off because the meth includes the carbon that's connected to the carbonyl. Okay, and that is methanoic acid. Okay, have a go at drawing the ester that you think you're going to form. Okay, so your structure of your ester should look as it is on the board now. Exactly, and I explained that we were doing it opposite way round on purpose, because you may not get it in order of your acid plus your alcohol in your exam, so you need to be familiar with what part comes from what. Now, if you notice in the structure of your original acid, it's the one that has the carbonyl bond. Okay, so in your ester, it's going to stick with that carbonyl bond. Okay, and then it has the other oxygen connected, which actually comes from the alcohol, but you don't need to know that at this stage. So naming this ester, okay, what does our first part of the name come from? The alcohol, so it is propyl methanoate. Lovely. Okay, great. Why don't you try it for methanol and butanoic acid? Methanol plus butanoic acid. Okay, so naming this ester then, what have we got? Methyl butanoate. So methyl from our alcohol and butanoate from our acid. Great.
You just write H2 or don't draw.
Yeah, in the full structural equation you would have to draw all the bonds, so you'd have to draw hydrogen attached to an oxygen attached to a hydrogen, but in this case, no. Okay, what we'll do is we'll do our little practical now. So what we just produced there was ethyl ethanoate, which should apparently smell like PVA glue. The characteristic smell of our esters are sweet and fruity, and you can see the different combinations here, which we could make, but we're not going to now. Okay. So very quickly, let's have just a quick look at how we can do this esterification using an alcohol, but instead of using the acid, using acyl chloride. And acyl chloride is anything with this functional group. So this is what you draw in this space. It's got a carbon chain connected to a carbon a carbonyl, and instead of an acid or a hydroxyl group, our acid chlorides have instead just a chlorine atom. Okay, can we draw this in, please?
Where? It'll be.
At the top of page 17. R could represent a methyl group, an ethyl group could even represent a hydrogen, but this is the functional group that we need in our acyl chlorides. Okay, they are named in sort of in the same way as our carboxylic acid. So if we compare F with ethanoyl chloride, so here is ethanoic acid, which you could be drawing as I draw it, to see if you, or you could just be okay, so what we're doing is we're swapping our OH group.
Where are we drawing this?
Under the ethanoyl chloride. Oh, not that actually.
Wait, miss, where are you drawing this? Oh, right.
And another one goes here.
Yeah.
Okay, and then if you draw those just in two different colours, it just shows that's all that we've swapped. And so instead of this being called ethanoic acid, so ending in oic acid, we're now calling this ethanoyl chloride. Ethanoyl chloride, and that's how we name our acyl chlorides. Okay, can we listen please? So basically what you're doing is finding your longest carbon chain there is 2, and so it's ethan, and then you end in oil chloride. Just the same way as you...
If it's got a halogen?
Yeah, well, generally we use acyl chlorides rather than acyl bromides or anything, so yeah, it has to have particularly a chlorine group if it's an acyl chloride.
Then it's an oil.
Ethanoyl chloride, yep.